Hello everyone, welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about mass transfer through spherical system. Mass transfer through spherical geometry. Mass transfer through the spherical geometry. We will use an example in which water droplet will evaporating into the surrounding air. So our example in this lecture, we will use one example which is a famous example in which water droplet is evaporating into the surrounding air. So evaporation of water droplet into the air. We will make some assumption in this lecture. In this lecture we will make some assumption. The first assumption will be that the density of water, which will be denoted by rho A, which will be constant. The second assumption, the viscosity of water will be constant. The third assumption, that this process, the evaporation of water droplet into the air, will be a steady state process. It will be a slow process. We will assume that it will be a slow process. It will be a steady state process. The density of water will be constant. Similarly, the molar flow rate of water through the stationary air will be constant. So the molar flow rate, which is molar flow rate of water, will be constant. So there are some assumptions in which the density is constant, and similarly the droplet will be spherical. It will be spherical droplet. The water droplet will be spherical. So let's see. First of all, suppose this is a spherical droplet, water droplet. This is the surrounding air. This is the water droplet. It is denoted by A. There are two components in this system. One is the water and the other is air. The air is stationary. This is stationary. This is the stationary layer around the water droplet. The stationary layer of the air molecule around the water droplet. The air is stationary and it is component B. The water is non-stationary and it is diffusing into the air molecule which is around the water droplet. So there is also another assumption that component A is diffusing into non-diffusing component B. So the famous and the very good assumption is that the component A, or the water molecule, is diffusing into the air molecule, while the air molecule is not diffusing into the water molecule. So there is also assumption that component A is diffusing into the non-diffusing component B. So in this case the water is diffusing. This is a stationary layer. This is a stationary layer of the water molecule. So and this is the spherical droplet of water. Spherical droplet of water, and this is the air. This is the thickness. The thickness of this stationary layer is denoted by R. The water vapor is diffusing, the water vapor evaporating, and it diffusing into the stationary layer. When the water evaporating, it come to the stationary surface. When it come to the stationary surface, it enter into the stationary air molecule, and then it come out from the stationary surface. So there is no generation of water molecule inside the stationary layer. There is no consumption of water molecule inside this stationary layer. There is no accumulation of water molecule in this layer. So simply the water molecule will evaporate. It will come to the stationary layer. It will diffuse inside into the stationary layer, and then it will come out from the stationary layer, which is around the water droplet. So in this case, the material balance, which is the general material balance, will be equal to, as we know, the general material balance equation is input minus output plus generation minus consumption is equal to accumulation. There is no accumulation of water in the surrounding stationary layer, so this term will be 0. There is no accumulation. It is a steady state process, so it will be 0. There is no generation, there is no consumption. So simply input the water molecule which come into the stationary surface. The water molecule will evaporate. It will come to the surface. It will enter to the stationary surface, and at that time it will come out from the stationary surface. So input minus output is equal to 0, or input is equal to output, which is a steady state process. Water molecule coming to stationary surface will be equal to the water molecule coming out from the stationary surface. So water molecule, so component A coming into the stationary surface will be equal to the component A molecule which coming out from this stationary surface, which is around the water droplet. So input minus output is equal to 0. So we can further write this in the form of flux. Suppose this is the water, this is the air. The component A, the water is component A, the air is component B. The radius of the water droplet is, suppose it is RS. It is RS. And suppose this is the R, the radius of the surrounding stationary layer. This is the thickness, delta R, and this is the R plus delta R. So this is droplet, this is the surrounding air. So this is the RS, RS, this is the R, this is the thickness, this is the R plus delta R. The flux of A which passing through this layer is, stationary layer, is NA at point R. So because this is the point R, this is the point R, and this is the point, this is the point R plus delta R. So the flux at this point is NA R. The flux coming out from this point is NA R plus delta R. So similarly, the flux at this point, this is also, this point is also R. So this is the R point. Flux at this point is NA R. This is the thickness, and the flux at this point is Na. At this point is Na R plus delta R. This is the flux at this point. So the flux coming into the stationary layer is Na R. The flux coming out from the stationary layer is Na R plus delta R. So Na R minus Na R plus R is equal to 0. So we will write it from material balance, which is Na R minus Na R plus delta R is equal to 0. Now the molar flow rate, this is the flux. We know that when flux multiply by area, we will get the flux is nothing but mole per unit area per unit time. When it multiply by area through which the component is passing, then we will get molar flow rate, mole per unit time, which is denoted by molar flow rate N. So in this case the spherical system is used, so we will use the area of the sphere, 4 pi r square Na, which is the molar flow rate at point R, minus the molar flow rate at point R plus delta R in coming out from the stationary layer. So suppose this is equation number 1. Equation 1. Divide equation 1 by delta R, we will get 4 pi r square Na R minus 4 pi r square Na R plus delta R equal to 0 divided by delta R. Now let delta R tend to 0 and use the definition of first derivative. We will get minus d by dr 4 pi r square Na is equal to 0. Or we can write d by dr 4 pi r square Na is equal to 0. We know that d by dr of constant is equal to 0. So 4 pi r square, we know that the derivative of constant is 0. So from this relation we know that the 4 pi r square Na is constant and it is denoted by W. So area 4 pi r square, which is area into flux, smaller flow rate, and it is constant and it is denoted by W. So suppose this is equation number 2. Now the molar flow rate is constant as we have already assumed. So 4 pi r square into the flux of component A is equal to W, which is constant value, and which we have assumed that in our assumptions. So this is W. Now we know, we also assume that component A is diffusing into non-diffusing B. So for this case we will get that the total flux of A will be equal to Na plus NB. From mass transfer we know that the total flux is equal to Na plus NB into Pa divided by D divided by P. If there were concentration, then we will write Ca divided by total concentration. So in this case the water vapor is in gaseous form, the air is also in gaseous form, so we will use the partial pressure and we will use the relation that C is equal to P divided by RT. So Na is equal to Na plus Nb into Pa divided by P minus diffusivity of A, the diffusivity of water molecule into air molecule, divided by the change in partial pressure of A divided by in the R direction divided by RT. This is R because it is in the radial direction. We use the radial direction. This is the radius RS, the radius of the water droplet, and this is the R direction. So the spherical and sphere we use the R direction, not the Z direction or the Y or X direction. So in this case dP by dr. As we know that the air is not diffusing into the water, so NB is equal to 0. And after simplifying we get NA PA divided by P is E minus DAB dPA divided by dr into RT. So just further simplify it. NA minus NA PA divided by P minus DAB dPA divided by dr RT. NA minus PA divided by P minus DAB dPA by dr into RT. R NA P minus PA divided by P is equal to minus DAB dPA divided by dr divided by RT. R is the universal gas constant having the value of 8.314 joule per mole into Kelvin. T is temperature which is constant. It can be room temperature 298 Kelvin, or it can be isothermal condition. In this case we assume isothermal condition. We know in isothermal condition temperature is constant, so the temperature is also constant. It can be 298 Kelvin or 300. For simplicity we assume room temperature 298 Kelvin or 273 Kelvin, 0 degrees C. So Na flux of water molecule is equal to P dAB RT dPA divided by dr followed by P minus PA into minus. So this is P divided by P minus PA into RT. So Na is equal to minus P dAB P minus PA by RT Sorry, there was a relation Na minus Na PA divided by P dAB dPA divided by dr to RT. So Na is equal to P divided by P minus PA dAB divided by RT dPA divided by dr. We also know that minus dAB by RT change in the partial pressure divided by P minus PA into NADR. So this is P and this is the minus sign. So we can also write this relation. We can also further simplify. Na dr is equal to minus P dAB divided by RT. So suppose N2 ln, this is cancel, ln use the minus PDAB into dPA P minus PA. So PDAB divided by RT into dPA divided by, so NA minus P TAB divided by RT dPA divided by P minus PA. So we also know that from the previous case, we know that the flux 4 pi r square into Na is constant, which is W. So from this relation we know that Na is equal to W divided by 4 pi r square. So put Na is equal to W divided by 4 pi r square in this equation. Suppose this is equation A. So 4 divided by W divided by 4 pi r square into dr is equal to minus P dAB by RT dPA P minus PA. Now we know that the pressure changes with the R direction. Pressure of the water molecule changes with the R direction. So we will integrate dr with the passage of so PA with the R direction, the pressure of component A in the R direction. So W is constant, 4 pi is also constant, pressure is also constant, the total pressure TAB is constant, R and T is also constant. So in the R direction the pressure of A will be changes. So we will use the integral sign, which is W divided by 4 pi dr into R square integral minus P dAB RT. Now integrate this sign this side. We will get ln P minus PA. So W divided by 4 pi into dr divided by R square is equal to P dAB divided by RT, and applying the limit when R is equal to RS, suppose this is the RS, this is the surrounding air. When R is equal to RS, the PA will be equal to PAS. The pressure of water at this point will be equal to the vapor pressure of water at the droplet temperature, when R is equal to RS, then the pressure of A or the pressure of water droplet will be equal to the vapor pressure of the water at the water droplet temperature. It will be equal to PAS. When R tends to infinity, when R is very far away from the water droplet, the pressure of when R is equal to RA infinity, when R tends to R infinity, suppose RA infinity R infinity, then the pressure of A will be equal to PA infinity. when R tend to, this is the, in this place there is air, this is the air. So when R very far away, from the water droplet, there will be air molecule, there will be a bulk of air. So when R tend to infinity, the pressure of water will be equal to the partial pressure of water molecule in the bulk of air. So when R tend to infinity, the pressure of water will be equal to the vapor pressure, to the partial pressure of water in the bulk of air, and it will be denoted by PA infinity. So further simplify this, W divided by 4 pi, W divided by 4 pi P dAB divided by RT. W divided by 4 pi dr r square P dAB divided by RT ln P minus PA and to limit PAS PA infinity when R is equal to RS, PA is equal to PAS, and R tend to R infinity, the PA is equal to PA infinity. Now applying the limit, now integrate this equation, whole equation, under C, integrate it, W, and applying the limit 4 pi 1 over R is R infinity P dAB divided by RT ln P minus PA infinity divided by P minus PA S. So W divided by 4 pi 1 R infinity minus RS is minus. As we know that R infinity is very far away from the radius of the water droplet. R infinity is very far away. It is nothing but it is infinity. R infinity is nothing but it is infinity, and we know that 1 divided by infinity is equal to 0. So it will be equal to W divided by 4 pi into 1 over RS is equal to P total pressure diffusivity of A into B divided by RT ln P minus PA infinity P minus PAS. PAS W divided by 4 pi RS is equal to P dAB divided by RT ln P minus PA infinity divided by P minus PAS. So W divided by 4 pi 1 over RS is equal to P dAB RT ln P minus PA infinity P minus PAS. Now we know that this shows the relation between pressure and radius of the water droplet. This relation shows the relationship between diffusivity and the radius of the droplet, or the pressure and radius of the sphere. So Now we can write this relation in other form. Suppose equation D. Suppose it is equation number D. We can write this by W is equal to P DAB divided by RT ln E minus PA infinity. E minus PA into 4 pi RS. Now we know that the molar flow rate of water is constant, which is W, and we know that W is nothing but the molar flow rate of water, which was constant, and it is denoted by D and A, change in time, and mole is nothing but mass by molar mass, and mass is nothing but density into volume of the sphere. So the density of water into the volume of water droplet. Volume of water is in spherical form, so volume of the sphere, which is 4 divided by 3 into pi r s cube volume, and the density of this is the water, so the density of water is rho A, which is 1000 kilogram per cubic meter, which is constant. We assume that the density of water is constant, so is the density into the volume of water divided by the molecular mass of water, which is nothing but 18 gram. Molar mass of water is 18 gram. From the periodic table we can also check it. So d by dt. So W is equal to the volume of the sphere is 4 3 pi r cube, and we know that only the diameter and radius of the sphere changes with the passage of time. We know that with the passage of time, the water evaporating into the surrounding air, and its radius or diameter of the spherical water droplet will be decreases with the passage of time. So this is the radius changes, the diameter decreases, the radius decreases, so the W will be changes only with the passage of time, and the radius will be decreases with the passage of time. So this is the nothing but the 4 divided by 3 and 3 density of A, molecular mass of A, pi and d by dt, the rs cube. So it is further simplified. 4 by 3 pi, and this is the power rule 3 density, molecular mass, and rs square drs divided by dt. Let's cancel with this. It is 4 pi rs square less than 2. 4 pi r square into density of A divided by molecular mass of A into drs divided by dt, because with the passage of time only radius decreases, radius decreases. Suppose radius decreases with the passage of time, so this term will be negative because radius decreases, passage of time will be negative. This term will be negative because radius decreases and the mass of the mass of the water will be decreases with the passage of time. So W is equal to, this is, suppose this is equation number E and this is equation number F. Equation E and F. Compare equation E and F. Equation E and F. Equation E is 4 pi r square and equation F is P dAB divided by RT, 4 pi rs. So there are two equations, equation E and equation F. So 4 pi r square so equation W is equal to 4 pi r square density of A, molecular mass of A, into drs dt. Suppose this is equation E, suppose equation F. You can give any name to these two equations. Compare the two equations and simplify it. We will get, is the left hand side equal, so the right hand side will also equal. Now simplify the two equations. We will get, simplify these two equations, we will get a 4 pi, we cancel with 4 pi, 4 pi cancel with 4 pi, the r is cancelled with rs, and we will get P dAB RT ln P minus PA infinity P minus PA S, P dAB divided by RT, P dAB divided by RT ln P minus P infinity divided by P minus PAS is equal to minus Rs density, molecular mass, and to change in the radius with the passage of time. Now this is the final equation, and this equation shows us that the radius changes with the passage of time, and it also shows us that how much time it will take to completely evaporate the water droplet with the passage of time. So this equation shows us shows us that how the radius of the water droplet changes with the passage of time. So it is P dAB divided by RT and is equal to ln P minus P infinity divided by P minus PAS for RS into this term. So final equation is P dAB divided by RT ln P minus PA infinity P minus PA S is equal to minus 4 RS rho A molecular mass of A dRs divided by dt. So this is the final equation. Now this is the final equation. Now this equation we can further simplify this equation. We can further simplify this equation by this 4 is also cancelled in the previous case. So we can further simplify this equation by P DAB RT ln P minus PA infinity divided by P minus PAS into dt and to MA. Then we come to this side, MA, the density of A, and this is the RS, and this is the minus sign. Now integrate this with the passage of time. As the radius changes with the passage of time only and only, other term is constant. The density, the molecular mass, the pressure, which is 1 atm or 1 bar, the R is universal gas constant, T is temperature, which is constant, dAB is constant, and the other quantity are constant. So the radius of the sphere changes with the passage of time, and if we integrate this term, this right hand side, we will get minus R is here divided by 2. Take the limit. When time is equal to 0, the R will be equal to, when time is equal to 0, this is when time is equal to 0, the R will be equal to RS, the radius of the sphere. When time turn to some time, the radius of the water droplet will be RS dash. So from this relation we can also write. So MA rho A total pressure, which is 1 atm, dAB RT ln P minus PA infinity P minus PAS, and the time when time t is equal to 0, when time is equal to 0, the R is equal to RS. When time is equal to some time, the radius of the water droplet will be RS dash. So it will be equal to RS dash. So RS, when time is equal to 0, it is RS, and it is after some time, at a certain time, it is RS dash. So simplify this. T minus 0, it is time, and it is nothing but minus 1 over 2 sorry, this is minus 1 over 2 minus 1 over 2 RS dash square minus RS square. Now how much time it will take to completely disappear the water droplet, to complete evaporate the water droplet? If we wanted to complete evaporate the water droplet, as we know, with the passage of time, the water droplet decreases. So water droplet first was this radius diameter, at a certain time it was decreased, the diameter was decreased, radius was decreased, after a certain time it was further decreased, it was further. So how much time it will take to completely evaporate the water droplet? And this is very important in the evaporation of droplets in spray dryer, or the diffusion of component in the catalyst pellets. This phenomenon is very important when we wanted to dry milk particles in dryer. If we wanted to diffuse some component in spherical catalyst particle, then these phenomena are very important in these cases. So it is very important in catalytic process, in cracking, in petroleum process. So how much time will it take to completely evaporate the water droplet? So in this case, the radius of the water droplet, when the water droplet completely evaporates, then the time will be equal to T dash. Suppose when the water droplet completely evaporated, then it will completely evaporated in the time T dash. And when the water vapor completely evaporates, its radius will be completely disappeared. So its radius will be completely disappear. So Rs dash, which is the final radius, it will be completely disappear. If you wanted to completely evaporate the water droplet, then its radius will be, which is the final radius of the water droplet. The final radius of the water droplet will be 0, which is Rs dash. So Rs dash will be completely 0. This is completely or nearly equal to 0. So we will assume that Rs dash will be 0. So that is 0. Now the time will be equal to T dash. So it will be T dash. Now this time can be obtained from this equation. Suppose this is equation G or some other equation. We can also say equation J for simplicity. Any name can be given to this equation, and that time can be obtained by T dash is equal to 1 divided by 2 Rs square divided by 2 Rs square into rho A RT, density of A, universal gas constant, temperature, N2 divided by MA, molecular mass of water vapor, which is 18 gram, total pressure, which can be 1 atm or 1 bar, diffusivity of A and B, which is given in the table or from the graphs in the tables. Usually it is given in the table, or we can obtain from various correlation, and divided by ln P minus PA infinity divided by P minus PA S. And this is the time in which the water droplet is completely evaporated into the surrounding air, which is assumed to be non-diffusing component, and the water vapor is assumed to be diffusing component. So this is the final time in which water vapor will be completely evaporated into the surrounding air. So this is all about the diffusion of component A into non-diffusing component B, the diffusion of component A in the spherical geometry. It is very important in distillation and in cracking, in petroleum, and in dryer process. In the drying process, we also use this phenomena for milk drying purpose. So this is all about the mass transfer in spherical geometry. If you are new to my channel, please like and subscribe. Thanks.